Welcome everyone. Today I'm going to present our work about synchronization in distributed networks. We work in the synchronous round-based model, and the literature contains lots of algorithms working in this model. And a vast majority of them are designed in a context where each node of the network starts in the first round. We say that they assume synchronous start. As I will explain in a minute, this critical assumption may be quite problematic. The point of our work is finding a way to mitigate these issues. Let's consider a case where we need to execute two algorithms A and B sequentially. We can assume synchronous starts for the algorithm A. However, we may not assume that every node finishes executing the algorithm A at the same round. If each node naively starts B right after the termination of A, then the synchronous starts assumption will not be satisfied for B, and the established correctness results no longer hold. In this work, we try to circumvent this issue by providing a solution suitable for a large number of circumstances. In a previous work, this problem has been formalized as the firing squad problem. The idea consists in inserting between A and B a third algorithm. If this added algorithm solves the firing squad problem, then, in all of its executions, each node terminates simultaneously. Using the proposed terminology, each node fires simultaneously. As each node starts executing B right after the firing, we can safely assume that B starts synchronously. An algorithm solving the firing squad problem was proposed. Let's discuss the model in which the firing squad algorithm runs. Of course, it does not assume synchronous starts. It runs on a dynamic network. Any execution of the firing squad algorithm is described by a directed communication graph, where the edges specify from which node to which node a message may transit. Importantly, the communication graph is dynamic. The set of edges changes in each round. This dynamicity enables to capture a large space of possible behavior compared to a model where the communication graph is static. The central assumption under which the firing squad algorithm is correct is a strong connectivity assumption. In each round, the communication graph must be strongly connected. Moreover, the firing squad problem has been proved to be unsolvable without this assumption. In the literature, tolerating crash failures is often a highly desired property for distributed systems. In our model, a crash failure is represented as a permanent sink in the communication graph. Then, requiring permanent strong connectivity is incompatible with even a single crash failure. This is embarrassing. This problem may be tackled by providing a relaxation of the firing squad problem. Ideally, such a relaxation should require much weaker assumptions, while remaining useful to accommodate asynchronous starts. We propose the Mod K Synchronization Problem. Instead of firing simultaneously, we require each node to fire in rounds which are congruent modulo some parameter k. Let's give some situation in which this weakening is useful. Many algorithms are structured in a succession of k phases. Each node will start with its first phase. During the subsequent rounds, they will execute the second phase, the third phase, up to the kth phase, and they will indefinitely cycle between these k phases. The correctness proof of such algorithms usually relies on the assumption that every node will be in the same phase in each round. If such an algorithm is started asynchronously, This is no longer the case, and this will usually break correctness. In this situation, previously running the firing squad algorithm solves the problem, but this is overkill. If we only guarantee that the starts are congruent modulo k, then every node will be in the same phase in each round. A fair criticism of our approach is that the Mod K synchronization problem is not as universal as the firing squad problem. If we run sequentially some algorithm solving the firing squad problem and some algorithm B, then there exists a transition period in which some nodes have already fired, while some others have not. As the algorithm B has been designed with synchronous starts in mind, this unplanned transition period may lead to unsafe behavior. Charron-Bost algorithms are typical examples where this is not the case, as there is no possible progress until a sufficient number of nodes have fired. In other algorithms, a few simple tweaks may be sufficient to guarantee safety during the transition period. Now we get to our main results. We have shown that Mod K synchronization is solvable in dynamic networks. We use two fundamental assumptions. The dynamic graph must be delta-centered for some parameter delta, and delta must be known, in some sense that will be discussed later. Beside delta, no global knowledge, such as network size or identifier, is needed. Let's discuss what a delta-centered network is. Imagine that we select some node gamma and a branch of delta consecutive rounds in the dynamic graph, starting from node t to round t plus delta. Now we play the following game. In round t, the node gamma is colored red. In each subsequent round, each red node colors its outgoing neighbors red. Then, between round t and t plus delta, the red color will propagate along the network in a gossip manner. At the end of round t plus delta, we check whether every node has been colored. And the node gamma is said to be a delta-centered if starting from any round t with only gamma colored red, the whole network ends up being colored in round t plus delta. The dynamic graph is said to be delta-centered if it contains at least one delta center. Let's take a few examples. The class of one-centered dynamic graphs contain dynamic graphs in which some node gamma can color every node in just a single round. In other words, these dynamic graphs contain a permanent spanning star. The class of two-centered dynamic graphs is a superset of the class of one-centered dynamic graphs. But it also contains dynamic graphs in which some temporally link failures happen. The pattern is the following. By choosing a higher value for delta, we are more permissive. We allow more dynamicity, sparser graphs, and lower connectivity. To some extent, a higher value makes the algorithm safer. Now, I will try to dig a little deeper into the way we obtain our solvability results. We introduce the Mod K algorithm. This algorithm solves the Mod K synchronization problem, assuming that delta is smaller or equal than k, and k is strictly greater than 2. The algorithm itself is quite technical, and so is the correctness proof. In order to increase our confidence in the correctness of our results, we developed a formal proof in the interactive prover Isabelle. The whole proof is available on GitHub. As previously said, our algorithm is correct assuming that delta is less than k and k is strictly greater than 2. The natural question is how to get rid of these two annoying assumptions. First, notice that, by definition, if we solve mod k synchronization, we also solve mod k prime synchronization, where k prime is any divisor of k. A first consequence is that we can solve mod 2 synchronization with sync mod 4. This eliminates the second assumption. Moreover, regardless of the respective values of k and delta, it is always possible to find a multiple of k that is greater than delta. For example, is k equal 3 and delta equals 8, then sync mod 3 is incorrect. But sync mod 9 is correct and solves mod 3 synchronization. Depending on delta, the node can pick a suitable parameter k prime that solves mod k synchronization using sync mod k prime. This explains why delta must be known. Thus, regardless of the values of k and delta, the mod k synchronization problem is solvable. We also studied the complexity of our algorithm sync mod k. The number of rounds between the starting of all nodes and the firing of all nodes is bounded by a multiple of n times k, where n is the size of the network. At first glance, this sounds not very good, especially when n is high. However, this is a worst-case scenario. In a sense that is still to define, the average complexity is much better. In our initial version, each node running sync mod k needs unbounded memory. We also provided an optimized version of sync mod k that bounds the memory usage by log of n times k. A natural question is whether the problem is solvable without knowing delta. For example, using adaptive techniques. Unfortunately, we show that this is impossible. To conclude, let's compare the firing squad algorithm with sync mod k. Both algorithms run in dynamic networks. Both require a limited amount of global knowledge. However, the strong connectivity assumption of the firing squad algorithm has been massively weakened. In the fault tolerance framework, the firing squad algorithm does not tolerate any crash failures, whereas sync mod k tolerates up to n-1 crash failures. We believe that our algorithm provides a useful primitive for real-world systems. This work has been done as part of my first year of PhD. I would like to thank my PhD supervisors for their support and my reviewers for their benevolent returns. I was humbled to receive the Best Paper Award. I thank the jury for this distinction. I hope you enjoyed this talk. Thanks for your attention.